Hello guys, welcome to my channel. In this video, we will talk about the basics of stereochemistry. As you have already seen my recent videos that I have uploaded on my channel, but in this particular video, you will get to know about the Fischer projection. That means if your compound is three-dimensional and it like four different groups are attached to it, like first, second, third, and this one, the fourth. Now, if you will see these two arrows are different, that means in which these arrows they are showing different concept. Means when I'm watching at that particular compound, one atom is towards me and another is away from my side. So we will talk about one by one. So how the Fischer projection help us to understand the three-dimension structure of the compound. So first, when you will draw this Fischer projection of monosaccharide, give its wedge and dash structure for a molecule, then you will get to know that how Fischer projection or wedge and dash structures they help to understand the molecular model of monosaccharide. So let's start with one example. So this is a ball and stick model of three dimension of methane. Methane is CH4, means these four are hydrogens, and this is a carbon. This is hydrogen, this is hydrogen, this is also hydrogen, this is also hydrogen. So this is a ball and stick model. But in if you will draw the 3D structure formula within, then you will see like this. This is the chiral carbon to which the first, second, third, and fourth hydrogens are attached to it. So why these two different arrows? You can say the bonds are different. So we will look into it. Then why it is representation is like that. So in our next, so I'll let you know that how, first of all, this in chemistry, this three-dimensional plane or the molecule or any that, when you are going to put it on the paper, then how you will get to know its whole structure. So what was happened actually? So molecule exists, they are obviously in a three-dimensional plane, but to represent them on a paper, it's a very difficult task. How you will put that molecule on a paper? Paper is a two-dimensional. So what happened in 1891, Emil Fischer was there. He just devised a one method which give you the three-dimensional object that can easily be represented on a two-dimensional object by this projection. So what is the definition of that? It can be a method, first of all, of representing three-dimensional or organic molecule in two-dimensional structure on a two-dimensional plane, such as paper. So basically, it's a definition of Fischer projection. So horizons and the vertical lines are used to present the bonds. And the intersection of horizon and vertical line represent the center carbon atom. So if you like this is a Fischer projection in which this is a vertical line and this is a horizontal line. So the intersection is letting us know that there's a carbon is there. And isomer of different sugars in organic chemistry are most common representation of the Fischer projection, like glucose, fructose, sucrose, they all you can represent in a Fischer projection. Okay, so suppose this is a three-dimensional structure, how we can represent it? We have to represent like this. That means the 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 groups which are attached to the carbon, which are with the normal solid line like this. So they will be on this horizontal line, and the away and the close one, this one, y, and they will always be on the top and bottom. Or you can say one is away and one is close to the observer and one is away from the observer. So for this, you have to observe it. So somebody is observing it with this, then this A and B on the normal plane, C and D will be on a different plane. So benzaldehyde. Similarly, if you will say this H and OH like this and COH like this. So this intersection of this is called that the carbon. Okay. So we will say the carbon chain of the compound is projected vertically with the most oxidized carbon at the top. So in this, what will happen? the carbon which will be most oxidized form, that always be placed as the, like CHO, on the top of the vertical plane. Okay. And you can say this is a nomenclature rule for this. And the carbon lies in the plane of the paper, usually omitted. That is not important. So the intersection of the cross section asymmetric carbon, that you know, this is asymmetric carbon, wherever you will get it, it's a asymmetric carbon. But the horizontal lines or the bonds attached to the carbon are considered to be above the plane of the paper or point towards the observer. Okay, so we will do it one by one. That why flying wedge or wedge dash projection of the organelle are very important to us, because it's a very most common representation for three-dimensional molecule on a two-dimensional surface. So usually we use this with the calc centers. So three different lines are being used. First is solid wedge or thick line. It signifies that whatever the group is, that is towards the observer or above the plane. You have to remember one thing, that if you are getting this type of a bond, okay, so if you are getting this type of bond, then you will say it is above the plane, or you can say towards the observer. But if you are getting the continuous, you can say regular lines, simple, then they say they are in the paper plane, normal. But if you are getting like this dash, this type of arrow, it denotes that it is below the plane of the paper or away from the observer. So I think you all are clear. In the previous example, if you will say somebody is getting, in this example, if you will say, here A and B on the plane, normal, C is near the observer and D is away from the observer. Now, how we can represent this one? So similarly, they are saying it's very difficult, but don't worry. So because the German chemist Emil Fischer, they devised very simple notation, which is widely used nowadays also, and which allow us to represent the three-dimensional molecule on the 2D environment without any changing their properties. So here you can see here, this is the carbon which is here. Okay, this 2 and 3, they are normal lines, but this 4 is, suppose I is here. Okay, any I, okay, I, this is, and this 1 is away. It's from away, because it is dashed line. So this is how we can keep it. So Fischer projection shows sugar in open chain forms. And in Fischer projection, the atoms of sugar molecule, they are connected vertically by solid lines, while carbon and oxygen and carbon hydrogen bonds are shown horizontally. So stereochemical information is conveyed a very, very simple rule, that here, this is one, two, three, four. This is, we can represent like this. Most oxidized one will be there, and these are the normal, that carbon, oxygen, and carbon, hydrogen bonds are horizontal. That means 1 and 3, they are normal, but 2 and 4, 2 is close to the observer and dash line is away from the observer. So sugars that I've already told you that we can draw on. In sugar, you have seen CH2, CHO group is on the top. Hydrogen and normal oxygen, they are on the normal plane. So the enaldehyde group is written at the top, and the H and OH groups attached to it, they are on carbon, they are on the, one is light and one is on the left. The arrangement of the atom distinguish one stereoisomer from the other. You can check. Here OH is there, right side, but here OH is on the left side. So it is deglyceraldehyde, dextrorotatory, and it is levorotatory. Okay. So perspective formula, you can say simply, it is on the top, it is on the bottom, and this is on the horizontal. Okay. So if I say in this example, R-glyceraldehyde and D-glyceraldehyde, most oxidizable is on the top. Can you represent like this? This is chiral carbon. This is this one H, and this OH represented here, and this OH, this CHO. This CHO is a aldehyde group, and this is also CH2OH. Sorry, this is aldehyde. Okay. So these are two representation of R-glyceraldehyde, right hand, and the smallest also D-glyceraldehyde in the stereochemical nomenclature. Okay, so we were talking about that this vertical lines going into the plane and these horizontal lines go out of the plane. Okay, in plane and out of the plane. And the aldehyde groups, they will be more oxidized, so that's why they are always be on the website. So point of the C3 and C2 and C4 down, C2 and C4. They are on the down and sliding towards the C1. Very close. So below these are the three, I have already told you that monosaccharides and disaccharides and polysaccharides, they are being, represented in the form of Fischer projections, a very conventional formula in which you can check many chiral centers are there. Okay, so in which you can check how they represented this in zigzag style. But there's no need to know the zigzag style. But they are just saying that one is H is very close, OH is very far up, like this. Here OH is far close and H is far away, like this. Okay, so this is also D-ribose, and here OH is there, but here if you are representing, this is ribinose. And if it's in the second, if you are represented here, that is D-xylose. But if both the OH are in this side, then the lysox. So basically, they are looking, they all are diastereomers. Okay. And because I can quickly pick out the stereochemical differences according whether the hydroxyl group is on the left and right side. So we will check whether which type of the sugar it is. Okay. So basically, when you are studying hydrocarbon, the carbohydrates, and you can evident that 8 stereoisomers of this 2, 3, 4, 5 tetrahydroxypentenyl. Here, what will happen? You will check here aldo group is on the top because since oxidized carbon is an aldehyde and pentose, since they contain 5 molecules. Okay, that's why it is 1, 2, 3, 4 up to 5. And in this, how many three chiral centers are there? 1, 2, 3. So how many you can say how many stereoisomers will be there? There is a formula. What? 2 raised to power n. How many chiral center? 3. So 2 raised to power 3. 2 into 2 into 2 means 8. Yeah, these 8 isomers, they consist 4 set of enantiomers. And if the configuration at the C4 kept constant, 4 stereomers as they all will be diastereomers. Okay. This is another example. Here, this is aldehyde group, and there are 8 isomers will be there. You can check here. OH is this side, and but in the here's at this second carbon like this. So here both are. So like this. So because of the position of the hydroxyl ions, they are changes. So their structure, their properties will be changed, but they all are diastereomers. You can check here D-glucose, in which how it is D-glucose. Here is one carbon, second, third, and fourth. So here on the second carbon, OH is here. But in mannose, first and second carbon, OH is on the left side. But here, second and third. But here, all in ribose, all the OH are on the right side. But here, last two, fructose. So this is how we can, remember just the position of the OH, and you will get the different monosaccharides. Okay. So what is the uses of this Fischer projection that we have studied here? So basically in biochemistry, it plays a very important role, and we can also use them to show amino acids in other organic and even their IUPAC naming. We can do it. And in Fischer projection, you can also differentiate between L, means lever rotatory or dextrorotatory molecules. For example, by the definition, Fischer projection or it is a penultimate carbon of D-glucose is depicted with hydrogen on the left and hydroxyl on the right. Okay, so likewise in L sugars, hydrogens on the right and hydroxyl always on the left side. So this is how we can say. If hydroxyl is on the left, then it is L sugar. If hydroxyl ion is on the right, then it is D-glucose. So this is how we can differentiate between dextrorotatory and lever rotatory. And Fischer projection is also, in non-carbohydrates, we can't explain them, and so drawings are ambitious, and when confused we cannot go for the non-carbohydrate. Thank you guys. So in this video I will must say that you should remember that in stereochemistry every concept is very important, and to understand you have to start from the basics. So in all my videos, you can check for my other videos in which I have talked about the R and S configuration, isomerisms, what are the different terms are being used in stereochemistry, and basis of stereochemistry. Thank you for watching this video, and kindly subscribe, and if you can, and if you like this video, just comment. Thank you so much.